Hey there, and welcome to this next lesson on high level mathematics. So we're continuing with geometry today, particularly trigonometry, which is the study of triangles. And you might be wondering why we spend so much time studying triangles, specifically. Well, it's the most fundamental shape, really, the simplest one we can make from straight sides, because you couldn't have a two-sided shape with straight sides. And we've seen with polygons how we can divide it up into triangles. And so by understanding triangles, we can then understand many, bigger, more complex shapes. Also, we find many, trigonometric techniques can be applied to situations that might not first appear to have anything to do with triangles. So we'll see how that works as well. So let's look at the lesson plan for today. So we have right angle triangles here. Um, we're starting with right angle triangles, the simplest one. See how we can relate the sides and angles of a right angle triangle. Here we introduce trigonometric functions, which are defined by um, by a right angle triangle, and then we're going to use that to then relate the angles and sides of a general triangle, which is where we want to get to, really, not just right angle triangles, but all triangles. So then we're going to look at parallel lines, and we're going to see how lines being parallel, how we can relate various angles at the intersections of various lines. And then finally, we're going to look at bearings, which is a way of um, defining or looking at angle in a slightly different way, something that certainly has a historical relevance, but is still used, today for certain. So here we have right angle triangles. Let's start off with that. So first of all, we have Pythagoras' theorem, which is so here we have a right angle triangle. So Pythagoras' theorem relates to a right angle triangle, and what it does is it relates the lengths of the three sides, and we need to label our sides. First of all, we label the hypotenuse, which is the longest side, the one that's always going to be opposite the right angle. We label that C, and the other two sides we label A and B. And we have this relationship here, which might look familiar from our lesson on formulae. We saw how we could rearrange this formula. So relatively simple relationship between the three sides, which is great now because if we know two sides, we can then calculate the third by rearranging this equation. And we've got something similar for angles, because we know all the interior angles are going to add up to 180. So if we know two angles, we can work out a third. But say if we had a mix, say if we had an angle and a side, what can we do with that? And that's where then trigonometric functions come into play. And that's what their purpose is. They basically relate angles of a right angle triangle to their sides. So we have an equation that relates three sides, and one, for the angles, we want one that can relate sides and angles. So say if we have an angle here, like in the bottom left of that triangle, we've labeled it theta, which is just a Greek letter that is often used to denote a unknown angle. And we're trying to calculate that angle. So we label our sides, but we label them slightly differently here. We label the hypotenuse as just, HYP for hypotenuse. And then we label the other sides like this, OPP, which is opposite. So the opposite side of the angle. Um, Unsurprisingly, no, the side that is on the opposite side relative to that angle that we're looking at, and then adjacent, which is the side that is adjacent to that angle. So adjacent meaning directly next to, and you see like those two angles, like the hypotenuse and the adjacent come together to produce that angle. So you see the sides are labeled relative to the angle we're looking at, and that's important. And so we then have, say, our sine function. So sine of theta, our angle, is going to equal to the opposite over hypotenuse. So there's a historical reason why they're represented as like ratios, like you've got opposite over hypotenuse, like a fraction. But yeah, I won't go into that here. So basically, we take this unknown angle, we put it into the sine function, and what it produces is this ratio of opposite to hypotenuse. And we have similarly for the cosine function, and then for the tangent function, which we abbreviate to sin, cos, and tan. And so you see here, this gives us that relationship, an equation between an angle and a side. And we have an easy way of remembering it. That's what we call SOHCAHTOA. So SOHCAHTOA. And that's basically like SOH, meaning sine of an angle is equal to opposite over hypotenuse, and so on. And so if we put those together, you see we get SOHCAHTOA. That gives us an easy way to remember these little formulae. Now, say if I switch the angle like that, I put the theta up in the top right, Remember, like I said, the sides are labeled relative to that angle. So adjacent and opposite will change. Hypotenuse is always the longest side, so that won't change. But adjacent is now this vertical one, and opposite, the opposite side to that angle is now the bottom. So just be mindful of that. How we label this is going to change depending on the angle you're looking at. So let's say if we take a triangle like this. So this is a prime example of what I was talking about. So you see here, we only know one side, so we can't calculate the other two sides, using Pythagoras' theorem, say, because we're going to have two unknowns, and we know we can't solve that. But we do have a side and an angle, and this is where then SOHCAHTOA could be used to solve this, particularly, say, if we use tan, because here, uh, so you could use, there's multiple ones you could use depending on the side you're working out. Like, say, in this case, we're trying to work out the opposite side. So that's the vertical side that is opposite to the angle. So tan of that angle is going to equal to that opposite side divided by the adjacent side. TOA, tan equals opposite over adjacent. So then this gives us a little equation now for opposite that we can just solve. So if I times both sides by 2.10, we get this. And so now this we need to essentially plug into our calculator. You can't work this out on paper or anything. The tan function. So you should be able to see on your calculator three buttons, sine, sin, cos, tan. And if you press tan and then you put in 60, and then you'll probably need to close bracket. So, okay, that 60 is contained in that function. And you find out what the value of that is, and then you can times that by 2.1, and you'll get 3.64 is then the length of that opposite side. And so say now if we wanted the hypotenuse, we could use either, sin or cos. Or, but now we've got two sides, it's typically easy to just use Pythagoras' theorem. So we see the hypotenuse squared is going to be the sum of the other two sides squared. And if we calculate that out using our BIDMAS rules, and now we need to square root to get C, you see it's going to be just a bit over 4. And then finally, that last angle, we don't really have to use, SOHCAHTOA for that. We can just use the fact that all the angles add up to 180, so that must be 30. And so you see there, just from two pieces of information, we can work out all the other sides and angles of a triangle, or a right angle triangle specifically. In general, we'll see you actually need three pieces of information, but in a right angle triangle, your third piece of information is the right angle. So so we only need two additional pieces to then fix this triangle and work out what all the sides and angles are. So, say if we had a scenario like this where we have two sides, and we could use Pythagoras system, couldn't we, to get the remaining side? But say if we wanted the angles instead, we've got two angles in there. We know all the angles add up to 180, but there's two unknowns now, so we can't use that. Okay, so here is then another prime example of where we'd use SOHCAHTOA. So say if we have two unknown angles here, theta and phi, another Greek letter commonly used to label angles, but they could be labeled just x and y or something as usual. So sine of that angle phi. So remember sine of the angle is equal to the opposite side over the hypotenuse. So in this case, the opposite side is 2, and the hypotenuse is 4. So which ones you can use is going to be dependent on what sides you have available. So say if I wanted to use cos, I couldn't. Like cos of phi is then going to use the adjacent side, and the adjacent side to phi is that vertical side that we don't know. So that one wouldn't be of use. So you've got to make sure you pick the right one depending on the information you have. So sine of phi is equal to 2 over 4, which is half. Now, if we want to get phi, so we've got sine of phi. So you put this unknown angle into the sine function, and it produces an output, just like regular functions. We've learned about how those work. Now, what is actually going on inside that function is a bit complicated. Too complicated to study at GCSE level. So you just need to understand sine is this function that does a bunch of operations. It takes an input of a particular angle, and then it produces this output, and that output is this ratio of two sides. And so we can use that back to then work out what the angle is like this. So if we want to undo that, we have to apply the sine inverse function. So if we've got sine of phi equals a half, if we do sine inverse on both sides, then the sine inverse will cancel out on the phi, and we'll be left with just phi. So it's kind of taken us back. We've got the output of sine. The sine inverse will then take us back to the input. And so we have to then do sine inverse on the other side as well of the equation. So it's like the same thing we regularly do with equations. We do the same thing to both sides and it's fine. Um, so we then get phi is equal to 30. If you So sine inverse, how you do that on your calculator, you see on when the button that says sine, slightly above it in probably a different color, you'll see sine inverse. Typically that requires you to press the shift button in the top left of your calculator. So you press shift first and then press sine and it will come up with sine inverse instead. And then you use it like a function as usual. Put in your value of half, close your bracket, and press enter, and it'll give you the inverse. So it's basically what value, what angle would produce that value once going through that function. So we could do the same thing with theta. So now relative to theta, 2 is the adjacent side and 4 is the hypotenuse as usual. So we have cos of theta is equal to adjacent over hypotenuse, which comes out to 2 over 4 again. So we get cos theta is equal to half. We do a similar thing where we have to take the inverse of both sides and we can get theta is equal to 60. So you see there how that allows us from those two sides, we can work out what the remaining angle is. And finally, that like I said at the start, we could then use Pythagoras' theorem to work out that remaining side. So this time, we're trying to work out one of the other sides, not the hypotenuse, but one of the other two sides. And so you see, we've got the hypotenuse squared is equal to the sum of the other two sides. And it's one of those other two sides that is the one we're trying to work out. So it requires a little bit of rearrangement here. We've got b squared is equal to 4 squared minus 2 squared, which equals 12. And if we then take the square root, we get b is equal to root 12. Or we could simplify that to 2 root 3 using our understanding of surds. So that would be that side. Surds can often play a role really in trigonometry because you get this. You've got a lot of squares like a squared, b squared, c squared. When you try and solve, you're often going to get a square root. So, yeah, you might want to make sure your understanding of surds is strong. So let's move on to trigonometric functions. So we've seen what they are, sine, cos, tan. We've seen what they are by definition. So let's look at them in more detail. So first of all, look at some exact values. So say if we have our three functions, sine x, cos x, tan x. So we're just labeling our angle that is going into that function as x. And we consider a bunch of angles. And these are unique values because they're common angles we tend to come across. And they have specific values. Like you might notice if you play around with your calculator, most inputs that you give into your trigonometric functions will produce like an output that is just some long decimal number. Typically, it's an irrational number, in fact. So, and some of these will be irrational numbers as well, but ones that we can actually write exactly. So, first of all, notice the angles that we've picked here. They're not equally spaced. You have 45 in the middle, and then we go 15 either side, which is 30 to 60, and then 30 either side of that to 0 and 90. So those are our angles. And what we find is there is a pattern, like a sequence to the sine one for starters. And this is the only one we really need to remember. And you see this pattern, what it is we get root 0 over 2, root 1 over 2, root 2 over 2, root 3 over 2, and then root 4 over 2. So it's a relatively simple pattern to understand there. And then, we can simplify some of them. That one's going to become 0. The next one will be a half. The next two will stay the same, but the last one, root 4, is 2. So root 4 over 2 is 2. So we're only taking positive roots here in this range between 0 and 90. And so you see here, so these are our common values, but you see how they follow that pattern. So it makes it easy to remember. And that's all you need to actually remember because cos and tan can then be worked out from this. So cos is basically the exact same pattern, but in reverse. And then tan, there's an important result between sine, cos, and tan. Like tan is equal to basically sine divided by cos. So we saw that identity back in our algebra lesson on identities and other types of equations. And we'll see today where that actually comes from. But we can use it here. So tan is equal to the sine divided by the cos. So we get 0 over 1, which is 0, half divided by root 3 over 2. So you've got to do a little bit of fraction manipulation there. And you'll find that's 1 over root 3, and so on. And then that last one, we get 1 divided by 0. What is that going to be? Well, that's an undefined number because you can't divide by 0. And this will correspond to an asymptote. So you remember from our lesson on graphs, and we looked at reciprocal graphs, and you get these asymptotes, which are these lines that like your graph converges towards. You get lots of asymptotes with the tan function, and we're going to see what that looks like in a minute. So first of all, let's look at the sine function. So say if we draw an axis of x, and then on the y-axis, we're essentially drawing the value sine of x. And if we plot it, like I said, the inner workings of this, trigonometric functions are a bit beyond, GCSE level to learn about. But you could imagine generating a whole bunch of points, for 10 degrees, 20 degrees, 30 degrees, like we've done with quadratic graphs before. Plot a whole bunch of points, and if you draw a smooth curve through them, you find you'll get this oscillation. It just oscillates back and forth. And this goes on forever. If you go on to higher values of x, it will just keep oscillating back and forth forever. And what does it oscillate between? It's basically 1 and -1 is where this oscillates between. And we've just looked at one oscillation between 0 and 360, and you see it intersects the x-axis at these points, 0, 180, and 360, and then you have these peaks and troughs at 90 and 270. And so you see it kind of splits up our 360 degrees into four quarters, four 90-degree quarters, and see where it goes from 0 up to 1, down to 0, down to -1, back up to 0. So relatively simple to understand. So you do need to know this graph, know those key values, and how to sketch it like this, because we would need to read off this graph at some point. But just like we saw with the exact values, because of the relationships between the trigonometric functions, this is the only one we really need to remember. Because, okay, if we now want to look at the cosine function, it's basically the same thing as the sine function, but shifted across. And we'll see more of this when we look at transformations of graphs, where we kind of transform one graph into another that's similar. So we can kind of then infer where these values are going to be. It's going to intersect at 90 and 270. This trough is going to be at 1 at 80, and then we've got the peaks at 0 and 360. So now the tangent function is a little bit trickier. So first of all, let's look at the relationship between tan and sine and cos. So we saw that before, tan is equal to sine over cos, but where does that come from? It basically just comes from these definitions for sine, cos, and tan. So if we have tan is equal to opposite over adjacent, imagine we could split that fraction up like this, couldn't we? This is a really handy technique to be able to do. So you see there where we've got hypotenuse over hypotenuse, it would essentially cancel out there, wouldn't it? And it'd leave it opposite over adjacent, so it's still the same thing as tan. But if you look at each of those fractions individually, opposite over hypotenuse is basically sine, and adjacent over hypotenuse is cos. So hypotenuse over adjacent is going to be the reciprocal of that, isn't it? You're flipping it upside down, so it's basically 1 over cos. And so if we multiply these two together, you get sine cos, sine of theta over cos theta. So that's where that result comes from. A very simple result. And you might not necessarily need to prove this in an exam, but you will need to know this result and use it. And we can use it here to plot tan. So tan is a bit more complicated function. You might be aware of what it looks like. Maybe you've remembered what it looks like. But if you don't remember, you can work it out from this. And using, if you know what sine and cos look like, you can then use some reasoning to work out what tan is going to look like. So first of all, we know tan is going to have asymptotes, and it has asymptotes at 90 and 270. And the reason why that is because looking at that fraction, okay, it's equal to sine over cos. Whenever cos is 0, we're going to have an asymptote, aren't we? Because we're dividing by 0 here, and that's an undefined value. That's basically what produces asymptotes on a graph, usually. Also, we know it's going to intersect the x-axis at 0, 180, and 360, because this is where sine intersects the x-axis. And if sine is 0, then tan is going to be 0, isn't it? If it's equal to sine over cos. So now we can start plotting the graph. So starting from 0, we know it's either going to go shoot up like this or shoot down like that towards the asymptote, because that's what happens with an asymptote. But which way is it going to go? What we can do is look at the relative signs of sine and cos. So you might want to actually have a sine and cos graph in order, to compare to here. We can compare the signs of them. So in this region between 0 and 90, both sine and cos are positive. And so we've basically got a positive over positive. So we know tan is going to be positive. Likewise, in the next region, 90 to 180, sine is positive and cos is negative. So tan being positive over negative is then going to be negative. In the next region, we see sine and cos are both negative. So tan is going to be a negative divided by a negative, which comes out positive. So each section, we see it's going to be coming up from or shooting up to an asymptote. It's just a matter of knowing which direction is it going to go in. And we do it for the last one, where we see we've got negative sine over a positive cos in that region. It's going to become negative. So yeah, you might want to like get your three trigonometric graphs, sine, cos, tan, and look at them all side by side, and you can perhaps see these patterns, or use online graphing calculator and mess around with them, and you can see this relationship. So tan is it's a more complicated function. You're not asked about it so often as sine and cos. They're more important, but um, you can encounter it, and you can encounter the graph of tangent. Certainly at the higher level math. So and certainly higher grade questions. So you do need to make sure you're familiar with it. So let's look at general triangles now. How we can apply sine, cos, tan to general triangles to relate their sides and angles. So the key thing to remember here, first of all, is that Pythagoras' theorem and SOHCAHTOA, they only apply to right angle triangles, so we can't use them here directly. We want new rules that can act on all triangles. So, say if we have a triangle like this that isn't right angled, it's just a general one. We can derive what's known as the sine and cosine rule, two rules that we use for general triangles. We can derive them from SOHCAHTOA and Pythagoras' theorem by dividing this, a triangle up like this into two right angle triangles, which we can always do. And the proof of, how this works, I'm not going to go through here, but that's essentially where it comes from. And perhaps you can see that in the bonus material, why that works. And first of all, how do we label our sides and triangles? So, the sides and angles of the triangle. Well, we label it like this, where we typically label the angles like A, B, and C, like capital A, B, and C. And then the opposite sides use the same letter, but lowercase. Sometimes it can be the other way around, and you see uppercase for the sides and lowercase for the angles, but typically it's this way around. And so therefore, we'll have this one, the B, opposite sides, opposite angle and opposite side, B, and then same thing for C. So that's how we label our general triangle. So now the first rule we have is the sine rule, which is this. And what it is basically, okay, the sine of an angle divided by its opposite side is the same, regardless of what angle and its opposite side you use. So you see sine A over A is equal to sine B over B equals sine C over C. Or we could do it the other way around, because you see if you took the reciprocal of both sides, it'd be the same thing. So depending on what we're trying to work out, sometimes you want to use one or the other. So that is the sine rule, appropriately named because it uses a sine function. Second rule we have is the cosine rule, which is this one. So it's a little bit more complicated. And you see it starts off looking a bit like Pythagoras' theorem. We've got a squared equals b squared plus c squared. So remember, c is not hypotenuse here. We're not talking about a right angle triangle. A, b, and c are just general sides. But then you get this extra term of minus 2bc cos a. Now, how you remember this is, I normally remember this, is in the subject of the equation, the a squared, will match the angle. So you see the angle there is capital A, and we have a squared is the subject of the equation. And then the other two sides, in this case, the b and the c, fill in the space in between. You get b squared plus c squared minus 2bc. And now the thing is, this is cyclical. You can, permute these sides around because, okay, this is if we're focusing on cos A, but I could have easily labeled any one of the other angles cos A. So you find you can swap things around like this and have b squared as the subject, and b is your angle, and a and c will fill in the space in between in the cosine rule. And one last time, you see we can make c the subject if we wanted to, and a and b will fill in the space in between. And all these equations are equivalent. They're all applicable. So that's the cosine rule. We need to be familiar with those, and you perhaps need to remember these, or it might be given to you in the exam. You might want to check if that's included. So that's sine and cosine rule. So before we do some practice with those, let's look at the area of a triangle. So we used this before when we was looking at trying to calculate the area of a segment. Um, and you see here we had half AB sine C. So really, if you look at this shape, you see AB is basically two sides and C is the angle in between them. So if we've got two sides and the angle in between, that defines, a triangle, and we can calculate the area of that triangle using this formula. And again, we can commute the sides around. So we've got AB's, half AB sine C, but we could also have half AC sine B, and we could also have half BC sine A. So we can kind of, rotate around the values and it'd still work fine. Um, it's just using then different sides and different angles. So for a right angle triangle, uh, imagine if this was a right angle triangle, then we would get our usual formula of half base times height. Um, because sine of 90 degrees being a right angle, you find that's equal to 1. So imagine if we had sine 90 in that equation, you'd basically get half times by BC. Or in other words, base times height divided by 2. So you see how that formula for a right angle triangle, it kind of comes from this. So let's look at an example. So just a simple example here where we've got, remember, for a triangle, we need three pieces of information. So we don't have that right angle anymore. So here we have an angle and two sides. That's our three pieces of information. And we know from that, we can work out everything we want. So um, here we need to label our sides. We've labeled our angles. I've labeled them like theta and phi, but you might want to label them just your usual C and B. But I didn't want to reuse the same value because sometimes we label the points A, B, and C, and so then the angles A, B, and C is essentially the angles at those points. So here we can see that using the sine rule, if we wanted to calculate what theta is going to be, that angle at C, okay, so we've got sine of that angle is over the opposite side of 7.6 is going to equal to sine of 45 over 5.5. So we need to choose the values, uh, choose things such that it's using the values that we know. So in this case, we know we can't use, the angle at B because we don't know it, nor do we not know it's over the opposite side. So if we're trying to apply the sine rule here, we have to use those combinations. And then here we've got a little equation that we can then solve. We can then calculate what's on the right hand side there, do the sine inverse of it, and it will give us what the theta is, just as we did before. And we can do the same thing for phi as well, but we don't really need to because we can just use the fact that all the angles add up to 180. And then finally, say if we wanted to work out that remaining side, the opposite side to point B, so that's little b. So we could then use the cosine rule for that. Well, I mean, we could perhaps use the sine rule as well, but here we can use the cosine rule. So just so that we can see how each one's used. So you see here, we've got b squared, that side. Okay, so we know we're the opposite side, the 57.3, the opposite angle is what's going to go in the cosine. And then the other two sides are going to fill in the space in between. So we've got b squared equals 7.6 squared plus 5.5 squared, so on. And once we've done that, like you make sure you've got to use the cosine rule correctly. Now we've just got a big equation of b that we can solve. So on the right hand side, that's just one big calculation. We just need to use our BIDMAS appropriately. So I calculate all those squares and that multiplication of 2, 7.6, and 5.5. And I can bring all that together into 42.85. So again, you just got to know how to use that cos, cos on your calculator. And put this calculation in correctly. So that just takes a bit of practice. We can square root both sides, then get b, and yeah, you see it comes out to 6.5. So that's an example of using the sine rule and cosine rule. And sometimes you need to know what you can use and what you can't use. Like say if we look at a different triangle, and we're looking at like a special case in this one. But first of all, to know, looking at this first of all, what can we use, sine rule or cosine rule? And what we need to do, we need to be aware of the dependencies on the sine rule and cosine. So sine rule and is sine of an angle over a side equals sine of another angle over a side. So you see it uses two angles and two sides. So if we're going to use that, we need to know three of those values so we can then rearrange to find the fourth. So we need to have two angles and one side, or we need to have two sides and one angle, or something like that, that then allow us to work out the remaining one. Um, Similarly with cosine rule is a bit different because it uses three sides and one angle. So if we're trying to work out, like say if we've got three sides, we can then use that to work out the remaining angle. Or if we had an angle and two sides, we can then use the cosine rule to work out um, the remaining side. But if we've got more than one angle, the cosine rule is not useful because the unless like there's more than one known angle, because we can't use both that information in the cosine rule because the cosine rule only takes one angle. So things like that you need to be aware of. So you can always just try. If you try a sine rule and it doesn't work, you then okay try the cosine rule. Or if the cosine rule doesn't work, and then maybe try the sine rule. Vice versa. But if you can be aware of these dependencies, you can then pick the correct one to use straight away. So in this case, we've got two uh, sides and an angle. We're trying to calculate this angle here. We're told that theta is an obtuse angle, and that's going to be important in a minute. So let's label our triangle in the way we normally do. And here, think about it. We've got uh, two sides that are known, one angle that is known, and we're trying to work out another angle. So basically, we need a formula that is going to take two angles and two sides. Okay, what formula is that? Well, we can't use, obviously Pythagoras or SOHCAHTOA because that applies to right angles. We're just looking at sine rule and cosine rule. Well, it's going to be the sine rule, isn't it? The sine rule takes two angles and two sides. So, okay, we just need to apply it in the right way. So sine theta is equal, over its opposite side, 11.9, is equal to sine 19 over its opposite side of 6.4. We can then rearrange this and then solve to find theta. So we have to do, calculate that value on the right, plug it into our calculator, do the sine inverse of that value. But before we do so, see that value comes out to 0.605. If we now try and do sine inverse of 0.605, we find we get a value for theta of 37.25. Now, that should look funny because we was told theta is an obtuse angle. And remember, obtuse is basically between 90 and 180. So why have we got 37.25? Like, have we made a mistake? It's like, no, we haven't actually made a mistake in our calculations. Like, the calculation is correct. Um, the problem is due to an ambiguity with inverse trig functions and a limitation of our calculators. So the correct value would actually be this. And okay, let's look into why that's the case. So we see it comes out to, essentially 142.75 degrees or 143 to one whole number. Why is that the case? So we need to look at the original sine function again and how that works. So we got a value of 0.605. And if we draw across and see, okay, what inputs correspond to that output of 0.605, because that's the output of our sine x function, we then want to find what value of x would go as input, would produce that output. Well, we can see there it intersects the axis, the graph at 2 points. And so that's what we're getting here is basically the first point. And that's all the calculator does. It basically gives us at the first point. And so we've always got to be thinking, okay, is that actually correct? Because there can be potentially multiple answers. Like you see, there's a second solution there, which is at 142.75. And how we deduce that is using the fact that these two values are equally distant from 0 and 180 respectively. So just using like the symmetry of the graph. So we can see it's going to be 180 minus 37.25. So this is pretty much like the only example of this that you'll likely encounter where you get an ambiguity like this. And so you need to be able to just adjust your answer accordingly to get the correct one. There's another kind of ambiguity we could get, say with something like this. So you see we've got two sides here, and we've got an angle. And say if I label my points as usual, and say if we're trying to find that remaining side. So we've got two known sides, we've got an angle, and we're trying to work out the remaining side. So we need a formula that's going to use three sides and one angle. Well, that's the cosine rule, isn't it? So straight away we know we need to use the cosine rule here. That's the only thing that will work. And so we apply it appropriately. So you see the side we're trying to find is the opposite to point A. so it's going to be little a. But the angle we're using is 30. So the subject of the equation is going to be, the 4.9 squared, and the angle in the cos is going to be 30, and the other two sides are going to fill in the space in between. So you see how we get a squared uh, there on the right, and we're going to get an a in that, cos term. So a little bit trickier, this one. So this is more like an advanced question we'd get. If we calculate each of the squares, remember cos 30 is one of those exact values that we saw in the table before, which is root 3 over 2. And if we plug that in, you see we get this third, 7.2 times root 3. So we're getting quite complicated numbers here. But if we rearrange this, you should be able to see this is basically just a quadratic of a. The coefficients are a little bit tricky, but it's still a quadratic, so we can just apply the quadratic formula here. And if we do so, you see, we've got to just be careful when we plug things in. When we do b squared, so okay, so we're going to get 7.2 squared times 3, because root 3 times root 3 is going to be 3. So yeah, just be mindful when you're plugging things in, and then when you put this into your calculator, and you get two answers. Now, okay, so we're getting two possible answers, and which one is the correct one? Typically in this scenario, you will get one solution being positive and one being negative, in which case you just ignore the negative one, because we're talking about a distance here, and you can't have a negative distance. That doesn't make sense. But you see here, we've got a scenario where we get two positive solutions, and it's like, okay, this is like a rare case that can happen. And what do we do with this one? So we need to use just a little bit of intuition here. Like, so you look at this graph, this illustration of the triangle we have. We can see it's going to be 9.6 in this case. Like 2.9 is too small. So 9.6 is actually the correct one. But it's like, okay, but why do we get this other solution of 2.9? It's not just like an ambiguity of a, inverse function like we saw before. This is an actual viable answer. Like, why do we get that? And the reason why we get that is because look closely at this triangle that we have. We had 30 degrees at the top. We had a side of 7.2 and a side of 4.9. That was the information we began with. Well, look, I could morph this triangle to produce this triangle where I haven't changed any of that information. We've still got the sides of 7.2 and 4.9. The top angle is 30. And you see we get another triangle with a side length of 2.9. So, and that's why we get two possible answers, because there's two triangles that could correspond to that information. So yeah, a bit of an obscure case you could come across there, but I want to make sure, yeah, we've got all bases covered. So when you get two answers like that, typically one will be negative and you can just eliminate it. But if they're not, then you've got something like this, and you might have to sort of imagine which one is actually the correct one. So just to summarize, remember before I was saying like the kind of information you need for a triangle. You need three, like for a general triangle, you need three pieces of information. Or for a right angle triangle, you need two, because your third piece is the fact that it's a right angle. And that's then enough information if we use the appropriate rules to solve all sides and angles in that triangle. So here, three sides is good. Two sides and an angle is good. We can work out everything else. One side and two angles is also good. We can work out all other sides and angles. However, one caveat to this is if we have three angles. We can't work the sides out from three angles alone. And the reason why, because I can do things like this where I expand, I can make the triangle bigger, and I've changed all the sides there, but none of the angles have changed. And likewise, I could shrink it and all the angles would remain the same, but again, I've changed all the sides. So you can't, so those angles would correspond to like an infinite number of possible triangles. So we can't use them to solve the sides of a triangle, because those sides could be pretty much anything. And you might want to try this yourself. If you define a triangle with easy angles, maybe 30, 60, 90 degree, or maybe not 90, but yeah, maybe 30, 70, 80 degrees. You have a triangle with those angles, and then try using your trigonometry. on it. So try using the sine roll, or even for a right angle triangle for that matter, you could use SOHCAHTOA and try and calculate the sides, and you find you won't be able to, and that's the reason why. So, okay, we've done the main bulk of what we need to know about trigonometry. So now we're just looking at a couple of smaller topics. So parallel lines, this is a quick one, just a few things we need to be aware of. So say if we have a line like this and it's cutting another line that's cutting at a right angle. If we have a parallel line, so those two blue lines are now parallel, which remember means they're going in the same direction. They'll never meet each other. That perpendicular bisector, uh, it will be perpendicular to both of those lines. And you see the distance between these two lines will be the same all the way along. If and we could just put any other line, like this pink line here. In general, the intersection between two lines, you find opposite angles to be the same. So these two angles will be the same, and these two angles will be the same. But when it's intersecting two parallel lines, all those angles around that intersection is going to be the same because those intersections are, even though it's two different intersections, they're exactly the same because the lines are parallel. They're going in the same direction, so they'll both cut another line like that pink line. They'll cut them both in the exact same way. Um, Now imagine this was graphs plotted on an axis, and I put in the equations of these lines here. Um, like what we saw before with perpendicular lines, it was to do, we can see if the two lines were perpendicular by looking at the gradients. And you can see here, like the blue lines and the green line, their gradient is equal, if you multiply them together, they're equal to -1. 3/2 times by -2/3 will get -1. A property of parallel lines is a lot more straightforward in that the gradients are going to be exactly the same. So you see here, we have a gradient of -2/3 for both of those lines. Which makes sense, isn't it? Because if they're both going in the exact same direction, the rate of change, the slope is going to be exactly the same, which corresponds to the gradient, doesn't it? So that's a few things to be aware of about parallel lines. So now finish up on bearings. So this is another way of looking at angles, and you just need to be aware of how we define a bearing. So and what a bearing actually is. So it's typically when we're looking at angles between points, and we want to know what is the angular distance, from A to B. Like as in, okay, if I'm at A, what angle, like if I want to point in the direction of B, what angle is that? So first of all, an angle doesn't really mean anything if we have like a reference direction. Kind of like with our graphs and axes. We need to have an origin and we need to set an x-axis and a y-axis, otherwise our coordinates don't mean anything, do they? And so if I said, oh, B is at an angle of 20 degrees from A, what does that mean? Um, so what we do is we draw a north line. And so that's the lines going straight up, which we can assume is just in the same direction for A and B. If A and B are close enough, they're both basically pointing straight up like this. Um, you might want to think about it. Like imagine like on a globe like the Earth, if we were at 2 points really, really far apart, the north lines wouldn't be going in the same direction, would they? So interesting thing to think about there. But here we're going to look at simple examples where they're close enough that the north lines are basically going in the same direction. So the bearing of B from A is this angle here. So you've got to be very careful with the word in there. The bearing of B from A. So that basically means if you're going from A to B. So if you're at A and you're facing north, what angle do you need to turn so that you'll be facing B? And then you could just go in that direction and it'll take you to B. So that's what a bearing is. It's a bearing is like a direction. What direction do I need to face relative to my north line? So the bearing of A from B will, so yeah, okay, so that's the bearing of B from A. The bearing of A from B. So if I'm at B, what angle do I need to go? It's not going to be this angle here. It's actually going to be this angle here. So we have, because if we change it up, if we measure one clockwise and one anti-clockwise, it's not consistent. So we always measure clockwise. So going from the right of the north line. And so this reflex angle is actually going to be the bearing of A from B. So it's like if you're at B, you're facing north. How much do I need to rotate such that I'll then be facing A? And that would be the angle I need to rotate. So that's what a bearing is. So let's look at like a little example. Say if we've got A and B here, and we wanted to, like, say if this is something we're drawing, like we might be drawing this on a map, and say if we've got the location of C, we know C is at a bearing of 45 and 330 from A and B respectively. So bearings, we always use 3 digits. So 45 degrees, we've met, we put that as 045. Just a little thing to note there. And so if C is at a bearing of 45 from A, then that means C must lie on this line. So this is the locus of all points from at 45 degrees, a bearing of 45 degrees from A. So there's that word again, locus. I mentioned that earlier. We're going to be looking at that later in the course. It's like basically all the points that are on that bearing, that direction. And then likewise at B, if we do 330 degrees bearings, which is going to be, again, reading clockwise, is going to be that way. So you can see it's basically 30 degrees to the left, but because the bearing is measured clockwise, it's 330. And so now we can use our like understanding, like what we've seen before with intersections of graphs. Like if C has to lie on both of these lines, then it must be at this point where they intersect. And this is a technique that is actually used in the real world for positioning. So say if like C was transmitting some signal, and A and B both receive that signal, and maybe they've got like a directional antenna that can detect what direction that signal came from, we could then use this to then determine where C is. So yeah, and that's a real life thing used. So that's a simple example. Let's look at one final example where we're actually trying to do some calculations and how does this tie into trigonometry. So say if we've got B and A here, and collectively they're trying to work out how far away C is. So they've worked out that they're 3.4 kilometers apart, and that B is at A is at a bearing of 110 from B. So say if we put in our north lines, that's going to be this angle here. So if you're at B, you turn 110 degrees and you'll be facing A. Now we could use that to also work out what is the bearing of A, uh, the bearing of B, sorry, from A, because using our understanding of parallel lines, like the north lines are both parallel, so they're both intersecting this line at the same angle, so that would be 110 there. If we had add 180, we can get that full turn there, which is the bearing of B from A, isn't it? But when we're actually trying to do calculations with trigonometry, we might want to just use this angle instead. So it's not a bearing, but this is now just an angle between the north line and that line joining A and B, which is going to be 70, because we just done 360 minus the 290 gets us 70. So now finally, okay, if we've been given bearings of C from A and B, how could we now use this information to calculate how far C is from B and from A? So first of all, if we draw those two bearings in, so you see a bearing of 30 from A, you see it's the north line, we turn 30 degrees and it's going that way. From B, it's a bearing of 70. So you see that 110 degrees we had, we're now, that line is essentially going to split it up into 70 and then 40. And so now you might be able to see we've formed a triangle here. And we've managed to work out what some interior angles are. Like the interior angle at B is 40. The interior angle at A is 100, 70 plus the 30. And we've got that side between A and B. So, okay, we've got two angles and we've got a side. We know that's enough information to work out whatever we want here. So we want to try and work out what are the distances. So first of all, this angle here we could easily read off if we want to, because we know the other two angles, 100 and 40, so the remainder must be 40 as well. And then we could use, say, the sine rule to work out the side length A, so the opposite side to A. So that's the distance between B and C. A over sine of its opposite angle, which is 100, is equal to the 3.4 divided by the sine of its opposite angle, which is 40. So we've got an equation of A here that we can now solve. And if you solve that by times of both sides by sine 100, and then, you just got to calculate what that is, and you'll find it comes out 5.2 kilometers. Finally, the B, which is the opposite side to point B, which is the distance AC, the distance between A and C. We can do a similar thing. And you see we get sine 40 on the bottom of both of those fractions. So that cancels out, and we just basically get b equals 3.4, which you might have expected to happen because you see this is basically a big isosceles triangle, isn't it? Because we've got two angles of 40, so therefore BA is going to equal to A to C. So it comes out to 3.4 there. So there's an example of using trigonometry in a problem that might not have, at first glance, look like it'd be trigonometry, sorry. Right, okay, so that's enough here for today because it's quite a long lesson, but that's trigonometry, quite a big and important topic. Um, Here's a fun fact for you. So, you know that angles in a triangle don't always add up to 180. Okay, that might sound like, blasphemy almost, because we always think, they do add up. But that's only on a flat surface. So a triangle like this, you see, yeah, they do. But on a curved surface, you find they can add up to more or less than 180, depending on the shape. One example of a curved surface would be like the surface of the Earth. And you find if you had a big enough triangle, um, the angles will add up to more than 180, like in this case. And this was precisely what early, shipfaring, captains um, realized when they did a bearing between one point, another point, another, and back to the start. It would the angles wouldn't add up. And this was one of the earliest ways, mathematicians determined the Earth wasn't actually flat and was in fact round. I mean, they didn't know it was necessarily a sphere, but they knew it wasn't flat because otherwise, the angles would add up to 180, but they didn't. So there you go. Fun, quite an interesting fact there, I think. Um, so here you go. Here's the takeaways for today's lesson. So we've just done all of trigonometry in one lesson there. I appreciate it was quite a big lesson, but there's a lot to get through. Next time we're going to look at transformations. So not too bad. We'll look at transformations of just geometric shapes and then transformations of graphs, which tend to be a little bit tricky, but hopefully I'll be able to, help make that clear for you. So, okay, I will see you then in the next lesson.